Alright, so in this video we will talk about 2's complement representation. The binary representation that we have already seen only allows for positive integers to be stored, right? There's actually another representation of registers that allows not only positive integers but also negative integers to be stored. Let me just show you those registers. So the normal binary registers that we have starts from 1 and they are just powers of 2. They increase in powers of 2. So 4, 8, 16, 32, 64 and 128. So as you can see, these are just powers of 2 over here, right? This is the regular binary representation, you can call it that, right? But when it comes to 2's complement representation, one change is made to this entire thing. Okay, the leftmost register that we have no longer has just positive, but it now actually will have a negative value assigned to it. Notice that we will just take the leftmost register and give it a negative value. Okay, and hence now this whole representation that we have over here is called 2's complement binary representation over here. Okay, so what clearly this allows us to do is it allows both negative and positive integer values to be stored. Alright, this is the purpose of 2's complement representation. Now, one thing that we are now interested in is how do we find the 2's complement representation, basically a representation that can fit in these set of registers and represent the respective number that is provided in the question. Okay, so as I've said, this allows you to represent negative as well as positive values. So let's take an example of a negative binary value and see how do we convert it into a representation using 2's that can be fit inside these registers. Okay, so let's do that. The first thing you would do is just take the positive version of this number, positive of the respective number and find its regular binary representation. Okay, so let's go ahead and do that. For that, I'll actually just copy the registers over here. Okay, so right, I have these registers, so I'll just take the the positive of the number that is provided to us. So the number is negative 80. I'll just take the positive of that number, which is 80, and try to convert it into the binary regular binary representation. Okay, so I'll take 64, I'll take 16, and the rest of them would be just 0, right? You can check it yourself and see that this is the correct binary representation of 80, right? So that's the first step. Next two steps, I'll actually just write down the next two steps and do it all together. So the first thing you will do is flip every 1 to 0 and 0 to 1. The third step would be, and I'm going to perform both the steps together, add +1 to the result of step 2. Okay, so let's just do this. Now the second step was to flip every 1 to 0 and 0 to 1. So I'll just consider this whole representation over here. Wherever I see a 0, I'll write down a 1, and wherever I see a 1, I'll write down a 0. Okay, so if we do that, the representation we are going to get is, for the leftmost 0, we will write down 1 instead, then 0, then 1, then 0, then 1, 1, 1, 1. Again, notice how each 0 has been changed with 1, and every 1 has been changed with a 0. Okay, now we will perform the third step. So we are done with the second step, right? Now we will perform the third step, which is to just add +1 to this entire thing. Okay, so we will just add +1 to the to the result of step 2. Okay, so I'll just add +1 to the rightmost bit. Let me draw a line over here. So you should know binary addition for this purpose. Okay, so 1 + 1, we know that's a 0 with 1 carried forward. 1 + 1, again that's 0 with 1 carried forward. 1 + 1, again that's 0 with 1 carried forward. 1 + 1 is again 0 with 1 carried forward. Now over here, that's just 1 + 0 is just 1, no carried forward. The rest of them don't really have a carry forward anymore, so we will just write them down like this. Okay, now the thing is that this result that we got over here, if you copy this result onto the next page and bring back the 2's complement binary registers that I had shown you over here, if you take those as well and place them on top of these 1s and 0s, now if you look at this, just like the way we would convert any other binary number to denary, we will just take these numbers whichever have a 1 beneath them and add them. This time, remember, on the leftmost bit that's 1, so we won't take 128 but -128. Then 32 is positive, 16 is positive. If we take all those numbers, the addition of all those numbers is actually just -80, right? That is exactly what we were expecting, to find the 2's complement representation of this negative number. And remember, this won't be possible if we were using the regular binary representation, right? Because there is no register that has a negative value, hence we cannot really expect any combination of 1s and 0s to ever produce a negative number. But with these registers and by performing these 3 simple steps, we have a combination of 1s and 0s, which if we place them beneath the 2's complement binary representation of these 2's complement registers, the sum of these sequence of 1s and 0s provides us with the exact, as you can see, the representation of -80.